good morning, good afternoon, or good evening, everybody, depending on where you are. My name is Li Qiao. I am a professor in aeronautics and astronautics at Purdue University. Today is my great pleasure to introduce our webinar speaker, Dr. Sili Deng, a rising star in the field of combustion science and materials and energy. Dr. Deng received his bachelor degree in thermal engineering from Tsinghua University in 2010, and then he received his master and PhD from Princeton University in 2012 and 2016. After that, he went to Stanford and did a postdoc for 2 years before he joined MIT as assistant professor. And currently, he is the Abilov Career Development Chair Assistant Professor in the Department of Mechanical Engineering at MIT. She received the Bernard-Louis Fellowship from the Combustion Institute in 2016, and her research areas span a wide range in energy conversion and material synthesis, especially her interest in understanding of combustion emissions, physics-informed data-driven monitoring of reacting flows, and carbon-neutral energy materials and flame synthesis of materials. So today she's going to talk about combustion plus X attempts, challenges, and opportunities, a topic I'm sure very interesting to all of us. So with that, Dr. Deng, please, I'll give the floor to you.
Thank you very much for the great introduction, Lee. And I would like to take this opportunity to also thank the organization committee, and especially the lead from Professor Zhu and Professor Law on this effort. And also I feel extremely honored to be able to speak at this webinar, especially after so many wonderful talks from my senior colleagues, and especially also in front of, or 1 week before Professor Igor Fopoulos give his talk. Well, since he's going to talk about the 100+ years of combustion research and the reviews on that, I thought as a junior faculty member who just started my own independent career, it would be nice for me to share with you some of our recent work, this couple of 2 to 3 years work on trying to bridge combustion with other areas, and specifically try to utilize the latest development in other areas to advance our knowledge on combustion, as well as try to utilize whatever knowledge we have developed in combustion to advance other disciplines. All right, so for those of you who work on combustion, I think it's not difficult to justify that combustion by itself is already very interdisciplinary. So take this combustion chamber, for example, right? We are interested in the mixing and reaction of the gases, of the fuels and the oxidizers. And during this process, actually the mixing is controlled by this multi-phase turbulent flow. And the reaction is has tens of thousands of reactions involved. So in terms of the chemistry and in terms of fluid mechanics, actually combustion has a very solid core in the science part. However, as engineers, we are interested in the power and electricity generation. So how we can design the system such that we can have efficient energy conversion from the chemical bond to the thermal energy and then to the mechanical energy and electricity. Combustion has its core in engineering as well. And of course, nowadays, people are talking a lot about the emission problems. So there's an intersection between combustion and policy, but let's do not go there yet. And of course, during the combustion processes, we want it to be as clean as possible. However, inevitably, we will have some undesired byproduct from combustion, such as NOx, soot, and SOx, etc. And in order to mitigate the pollution issues, the combustion scientists need to talk to environmental scientists, as well as people working in atmospheric chemistry, etc. So for those of you who do fundamental combustion research, including myself, at least I got my training in, and I share this research philosophy with many of my colleagues, is that the ultimate goal for us is to enhance the design and control of the practical combustion devices and systems. And we take this approach due to the complexity in both chemistry and flow transport. We want to take this approach as divide and conquer. What I mean by that is that we normally would study the chemical kinetics in laminar flames because the flow configurations are relatively well characterized. So we can focus on what's going on the chemical kinetic side. On the other hand, as long as we have such chemical mechanism or models, we can use those well-validated models in laminar flames to study the transport and interactions in turbulent flames. And this governs actually my training in fundamental combustion research back at Princeton. During my PhD, my work basically mostly focused on the laminar flame chemistry regarding specifically on the low temperature chemistry and the fuel soot interaction, the soot chemistry. And later on, I touch upon a little bit on the soot modeling in turbulent reacting flows. As I started my independent career, I was thinking, is it possible to add another dimension or several other dimensions to the problem, such that we can leverage the latest development in many other areas and combine that to advance our knowledge in combustion, as well as engineering combustion into other applications other than the normal or the traditional energy conversion, etc. So specifically in today's talk, I'm going to talk about several attempts that we can combine combustion with uncertainty quantification, materials engineering, as well as machine learning. So in the first part, I'm going to talk about how we can take away some of the knowledge we get from laminar flames and try to combine it with some mathematical tools to further help us understand the physical insights from combustion and the take-home messages. So for those of you who works on laminar flames or flame chemistry, this type of plot will be very familiar to you. And this is a so-called sensitivity analysis. So what sensitivity analysis is that it is try to understand how does the quantity of interest changes with the perturbation in the kinetic parameters. And in this case, we are looking at the quantity of interest as the laminar flame speed, as well as the extinction strain rate. And the parameters we're perturbing is a prefactor A in the chemical kinetics. So here is the result from the literature. It's a methane air flame. Phi equals, it's a fuel lean mixture and high pressure. And you can see that the laminar flame speed and the extinction strain rate are sensitive to a set of reactions. And very interestingly, qualitatively, they are sensitive to the same set of reactions. So if we want to quantify how much such sensitivity is, we can do the sensitivity analysis at perturbing the prefactor A and take the derivatives, so partial natural log of the quantity of interest over partial natural log of the prefactors of each reactions we are going to perturb. So essentially, this sensitivity is a vector, and the number of the components in the vector matches the number of reactions we perturb. So for example, if we're going to perturb the top 2 reactions, then the sensitivity vector has 2 components. If we are going to perturb top 10, then the sensitivity vector will be 10 components. So this is a qualitative trend that the laminar flame speed and extinction strain rate shares the same sensitivity sensitive reactions. However, if we do some play with the numbers and do the normalization, which is we take the we normalize the sensitivity vector by the length of this vector, and we can get this sensitivity direction. So very surprisingly, actually, we see these sensitivity directions of the laminar flame speed and extinction strain rate. They are quantitatively very similar. So how similar are they? Is that we can, because they are vectors, we can take the inner product of that. So taking the cosine product of that, and we can see that the similarity is actually very high. It's not, it's almost 1. We know that in cosine, if it's 1, it means they are perfectly aligned in the same direction. So this actually motivates our research. Why we see the similarity in the sensitivity direction, and whether this sensitivity similarity holds for various of fuels. So we formed 2 hypotheses. The first one is we think we are interested to see if the flame sensitivity directions are independent of the strain rate and where you are in the flame structure. The second one is we studied the methane. Is this trend still hold for many other fuels, especially for other hydrocarbon fuels or with oxygenated fuels, etc. So how we are going to test the hypothesis is that we're going to use the premixed counterflow flames that are familiar to many of you. And we are going to first study how does the sensitivity direction changes for the extinction strain rate, which characterize the response of the flame to the strain. And then we're going to see how does the sensitivity direction changes with strain, as well as where we are in the flame structure. And to our surprise, actually, we compiled this data from the literature, and you can see across various fuels, across various equivalent ratios and pressures. This is in total 26 cases we see, and we compute the laminar flame speed and extinction strain rate and try to see the sensitivity directions and take the cosine, the inner product of these 2 vectors, and realize that, okay, it's very close to 1. So we do see the cosine similarity or the similarity in the sensitivity direction holds for various fuels across many thermodynamic conditions. So after seeing that, we want to see how does this sensitivity direction changes with strain rate. And from this result, we found that it's independent of the strain rate. But let me walk you through the details of the analysis. So we are taking these methane flames, for example, and we can compute the strain rate and then the response of the flame indicated by the maximum temperature as this. So for those of you who has played with counterflow flames, you might realize this is the upper branch of the S-curve. And this point corresponds to the extinction strain rate. And basically, we're sampling along this upper branch of the S-curve and do the sensitivity analysis to see how does the maximum temperature changes with the perturbed kinetic parameters. And here, we are computing the cosine similarity by taking the inner product of the sensitivity direction sampled at various strain rate, and the reference is always the sensitivity direction measured at the extinction strain rate. And to our surprise, again, we can see that the cosine similarity is almost 1. very close to 1. Although there are some difference in the magnitude of the sensitivity, meaning that sometimes it's very sensitive to these reactions, sometimes it's not very sensitive to the kinetic parameters. And that makes sense because when it's very close to the equilibrium, the lower strain rate is not that sensitive by the, it's very sensitive to the thermodynamics, but not very sensitive to the kinetics. But the take-home message is, again, we see that the sensitivity direction within the strained flames is independent of the strain rate. And similarly, we are investigating the sensitivity of the sensitivity direction to the flame structure, or in other words, where we are in the flame coordinate. So here, again, it's an example of the methane flame. And now we are sampling, we are looking at the specific strain rate of 500 per second. And you can see that this red line is the direction. You can see overall, it's also close to, it's also higher than 0.9 with the full scale of 1, right? So you can see it's almost have a universal sensitivity direction. And some of you might notice that, okay, there are points where it dropped below the 0.9, although it's still quite high. But you can also see that at those points, the normalized magnitude of the sensitivity vector is actually close to 0. Meaning that if you assume a universal sensitivity direction, the uncertainty that you bring is actually negligible. So we basically, the take-home message in this slide is actually, we do have a universal sensitivity direction independent of the flame structure, independent of where we are in the flame coordinates. So combining this slide with what we just saw in the last slide, we do see a universal sensitivity direction that is independent of the strain rate and independent of the flame structure. And we naturally ask this question, so what? So here I'm going to show you some implications of these universal sensitivity directions. So we are interested in the uncertainty quantification of the chemical kinetics, potentially in the, of course, we can do this type of study in laminar flames. However, when we bring the story to the turbulent flows, it will be very difficult because the computational costs will be very high. So we wanted to see if we can have any insights from the laminar flames that we can migrate those knowledge or transfer those knowledge to the uncertainty quantification in the turbulent reacting flows. So here is a showcase. Let's say if there are two kinetic parameters we're interested in to see their influence on the temperature sampled at 2 locations in the flow field. So X1 and 2 are the 2 locations. Delta 1 and 2 are the perturbations to the kinetic parameter prefactor A's of 2 reactions. So based on the definition, the temperature perturbation can be expressed by the sensitivity and the perturbed kinetic parameter. And mathematically, you can translate this into the sensitivity direction times the magnitude. And similarly, you can do the same for the perturbation at another location within the flow field. Because we just summarized, there is a universal sensitivity direction. So essentially, this tilde part is equal to this tilde part, which is shared in these 2 upper equations. So we can define a universal parameter C that represent this sensitivity direction. This sensitivity direction times the perturbation. So we can represent the change in the temperature at location 1 as this one, and the change in temperature at location 2 as this one. And we can see they share the same parameter that we are going to sample, right? And when we do the uncertainty quantification, what we do is actually try to see, try to perturb the kinetic parameters multiple times and try to see how does the response of the flame depend on the perturbations of the kinetic parameters. And in this specific case, I'm showing you a two-dimensional perturbation. However, in real combustion simulation, we are dealing with thousands of reactions. Of course, we cannot do the uncertainty quantification on the thousands of them, but it's very likely for us to perturb the top 10 or top 20 reactions. So we were talking about a dimension of 20 dimensions. But now we know, since there is a universal sensitivity direction, instead of perturbing in 20 dimensions, for example, we now can lump all those parameters on a single line. So we are only perturbing one direction. So you can imagine how much computational cost can be saved based on this argument and the take-home message we can get from the laminar flame studies. So in summary, we do identify at least in the laminar premix flames, there is a universal sensitivity direction, and that is true for various fuels, chemical models, equivalence ratios, and pressures. And what the take-home message would be is that it can enable us to do the fast sensitivity analysis in turbulent premix flames, at least for those where we can utilize the knowledge from laminar flames. For example, for a lot of turbulent combustion models, we're using the flamelet-based models, where we presume that the flamelet structure still holds. So the universal sensitivity direction should still hold for those cases. However, we also notice that it will be an open question in the community whether such universal sensitivity direction still holds for the broken reaction zones, where we have local extinctions and the laminar flame structure does not hold anymore. All right, now let's switch gear to the materials engineering. I came into this area when I did my postdoc with Dr. Xiaolin Deng at Stanford University. We find it very interesting that although most of the combustion scientists will focus on the gas phase reactions, actually there are heterogeneous reactions, solid combustion in combustion research as well, especially on the metal-based energetic materials. And my host, Dr. Li Xiao, actually works on these topics as well. So I'm going to show you our recent attempt on trying to combine the knowledge from materials engineering to the energetic materials study in combustion. First, a little bit on the background of the solid energetic materials and specifically the aluminum fuels. As you can see from this graph, actually it documents the element or a metal or semi-metal element and see their heat of oxidation evaluated at two metrics, the gravimetric metrics and the volumetric metrics. And to put these values into context, we can compare with the energy density of gasoline. And you can see that for aluminum by itself, it almost double or triple the volumetric energy density compared to the gasoline. And also we know that aluminum is actually well abundant in the earth. So historically, it has been used for solid rockets and solid propellants, some of the explosives. And many of you might be familiar with the thermite reaction, that term as well. And also in the pyrotechnics, people have been used this aluminum as the energetic materials. And a natural question for us is that we want to see how we can enhance the ignition and combustion of aluminum, and specifically under current situations where we wanted to mitigate the emission from carbon-based fuels. And you can see the aluminum-based fuels does not have these emission problems. So can we make use of this combustion of aluminum and try to not only focus on the defense application, but also can we use this for civil applications. But first, let we go through some of the issues of aluminum combustion. The main issues are the ignition and combustion. And basically, you can see as the diameter of the aluminum particle changes, actually the ignition property deteriorates, right? You need a relatively high ignition temperature compared to the gas phase reaction that we are familiar with. And the burning time actually increases by orders of magnitude as the sizes goes from the nano size to the micron size. And the dashed line here actually shows in practice, we normally use aluminum particles larger than 20 microns or 50 microns-ish. We are far away from the nano-sized particles. So the challenge is the micron-sized aluminum particles have relatively high ignition temperature and sometimes long burning time. Of course, it depends on the application. Sometimes you want to have a longer and relatively slow heat release. But sometimes when you talk about propulsion and explosion, you want to have a really condensed heat release. So how do we deal with this high ignition temperature and long burning time? It's the question we want to address. So let's briefly go over some of the current study, try to enhance the ignition and the combustion properties of aluminum combustion, especially the micro aluminum combustion. The first solution is quite obvious. Okay, if the micro aluminum has certain drawbacks, can we go to the nano size? And the reason is yes, we can. However, the nano size not only would be quite expensive to manufacture, but also, as you can see, all of these, because aluminum is relatively active and reactive, so all the natural aluminum actually would have a natural oxide layer coated at the surface of aluminum. So if you think about this, when the size shrinks to nano size, we know that nanomaterials have a relatively larger surface to volume ratio compared to the bigger size. So you can imagine there is a larger percentage of aluminum oxide at the surface of aluminum in the nano-sized aluminum particles compared to the micro-sized counterparts. As you can see from this figure, right, when the diameter of the particles shrink to 20-ish, right, almost 80% would become the aluminum oxide, and they cannot be burned anymore. So yes, we might see the reactivity enhanced by using the nano-sized aluminum. The total available aluminum would be reduced when the size shrinks. Then others have tried to coat aluminum with other reactive metals or coat it with fluoride coatings to remove the oxide layers and also reduce the product agglomeration to enhance the combustion, to shorten the combustion burning time. And some others also try to blend aluminum with other nano-sized reactive materials, etc. So with all of these fantastic background, our question would be, can we enhance the ignition and combustion of aluminum without lowering the composite volumetric energy density? So we do not want to introduce a lot of dead mass, not only for this one, but also here, if you are introduced a lot of metal oxide as the oxidizers, you are taking away a lot of the mass, right? So we are trying to get the input from the material scientist or material engineering to our combustion community. So in the following, I'm going to share with you some of our recent attempts. I think maybe covered in 4 papers. And the first attempt is that we try to improve the mixing between the oxidizers and aluminum to enhance the ignition and combustion properties. And as I mentioned before, a lot of people are experimenting with aluminum and fluoride polymers because they can reduce agglomeration. However, mixing aluminum with the fluoropolymer imposes certain challenges to us. Basically, this is a very viscous fluid, and you are trying to disperse nano or micro aluminum particles or nano aluminum particles into the viscous fluid is actually quite difficult. As you can see from the SEM images and the EDS on the elemental mapping, you can see all the aluminum is cluttered here, and the fluoropolymers are outside. So they are, although globally they're mixed, locally they're still separated, which would inhibit the ignition and the combustion performance. And also this will, because of the separation, it will reduce the mechanical strength of the composite as well. So our proposed solution is that we want to bring the technique developed in materials engineering on the surface functionalization, as well as the micro-emulsion technique to enhance the mixing between aluminum and the fluoropolymers. For example, just to very briefly go through this technique is that after the surface function, we can disperse aluminum in, let's say, the solvent number 1. And we can dissolve the fluoropolymer in solvent number 2. And then we can mix this solvent number 1 and number 2 with the micro emulsion technique. So in that sense, we are mixing 2 liquids instead of mixing particles to a liquid. And because of the micro emulsion, you can see that the aluminum particles are monodispersed in the solvent. And later on, when we cure the polymer, you are expected to see a better displacement of the distribution of the aluminum inside the polymer matrix. And to skip some of the details and directly bring you to the conclusions, you can see that this is an optical image. This is a mechanical mix. So just directly disperse aluminum in the PVDF polymer. You can see the color is uneven, meaning that there's a lot of polymers and separated from the aluminum, right? After this is a same material but used micro emulsion technique, and we can see the color is more uniform. And from the detailed SEM and EDX images, we can see that the particles actually are embedded in the polymer matrix more evenly and more uniformly. And we also tested the combustion and ignition performance in the traditional constant volume combustor. And you can see that the ignition delay time gets shorter when we use this micro emulsion technique. And also we achieve a higher pressure increase, which indicates a higher combustion temperature and a larger gas generation from the combustion of the energetic materials. And also from this bomb calorimetry, we can see the total heat release because all the materials are the same, right? So all the improvement in the heat release is due to the manufacturing technique. So we talk about, okay, we can enhance the mixing between the fuel and oxidizer. Here we are talking about maybe we can utilize or borrow some of the techniques that are often used in the wet chemistry synthesis, in material synthesis to our energetic materials and try to engineer the interfacial connections between the fuel and oxidizers. Here we are trying 3 different methods. This is a traditionally mechanically mixed particles, and this is a precipitation method in the liquid phase. And this is a displacement method using the electroless deposition of the solvent to the surface of the energetic materials. And you can see clearly the manufacturing method or the synthesis method has an influence on the morphology of the obtained composite of energetic materials. The coverage is different, the dispersion is different, etc. And again, we are characterizing the performance in the constant volume combustion chamber, as well as in the bomb calorimetry. And the take-home message is indeed with some more advanced synthesis method compared to the traditional method, the ignition property as well as the flammability actually all gets improved if we are using the more advanced precipitation or the displacement method. And also the heat release gets improved, meaning that the combustion efficiency gets enhanced with a novel synthesis method. So we engineered the mixing, we engineered the interface. How about we use some of the knowledge of doping or bringing additives to the energetic materials and try to enhance the ignition and combustion performance of aluminum. So here I'm going to show you our first attempt on bringing the 2D materials, graphene oxide, into the game. So nowadays there's a lot of research on the 2D carbon-based 2D materials. And specifically, we chose the graphene oxide because it will have a high light absorption so that we have this potential of optically ignite our energetic materials. And of course, the 2D materials have a relatively large specific surface area. And specifically with the GO, it has the disproportionation reactions upon the flash ignition, which is exothermic. So it can contribute to the ignition energy of the energetic materials of aluminum that we are interested in. So we expect to see that with the addition of a graphene oxide, the ignition and combustion behavior of aluminum can be enhanced. And we test our hypothesis in this flash ignition apparatus. So we have a flash tube and we have a glass slide put on that, and the particles will get just loosely put on top of the glass slide. And what we could see here is that upon the flash, right, GO can be ignited. However, if we are using just pure aluminum, they cannot be flash ignited. And just by mixing only 3% by weight of GO, aluminum can be ignited. So just with 3% of addition of GO, we can see the ignition of aluminum. And with 20%, you can see the ignition is actually very strong. And compared to GO itself, because most of the, after ignition, most of the heat release comes from aluminum, you can see it's really strong. And compared to what's being documented in the literature, the common additive of tungsten oxide, you can see with tungsten oxide, you first need to have a lot of additives. Second, you didn't enhance the ignition by a lot. But compared to that, our GO additive, actually, we can use only a little bit of GO and to enhance or to reduce the ignition energy needed by 20% or by 40% or so. And further, we were thinking, okay, the 2D materials works, the graphene oxide works. How can we bring some of the fluorinated additives into the system, and whether we will achieve any synergistic effects from that. And the reason why we're interested in the fluorination, as I mentioned previously, is first of all, it can remove the oxide layers of aluminum, and it can prohibit the agglomeration of the products. And another reason is demonstrated here is that in general, the fluorination has, compared to the oxidation, it will release more heat. So our hypothesis becomes, if we put some of the fluorinated graphene additives into the system, we will expect to see enhanced ignition and combustion properties of the previously synthesized aluminum and GO composites. And indeed, we can justify our hypothesis in the experiments. And to our surprise, actually, there is a synergistic effect by combining the GO and the GF. So what does that mean is actually after putting in the graphene fluoride, actually the performance of the final composite is better than the composite of aluminum MgO or aluminum MgF. So there is a synergistic effect going on here, meaning that the graphene oxide, upon the flash ignition, will release heat that facilitate the dissociation of the GF. And this one will, after the dissociation, it will generate some radicals that further enhance the disproportionation and combustion of GO. And they altogether provide the ignition energy for aluminum and some radicals to further oxidize the aluminum and remove the oxide layers of the product such that the reaction can continuously going on. So the take-home message is, yes, with the addition of GO and GF, we can see a very clear trend that we have an increased pressure rise as well as a strong emissions due to the combustion of aluminum. All right, and so we already summarized this. We can bring a lot of the techniques from materials engineering into combustion and try to develop the metal-based energetic materials. Some future work definitely needs to be done because in combustion, we are focusing mostly on the homogeneous reactions in the gas phase. And the understanding and modeling of the heterogeneous reactions in the solid phase actually is very challenging. And how we can turn this carbon neutral energetic materials for civil applications, it requires a lot of effort, since what we talk about can be done in the lab. However, how we can efficiently and cost effectively to manufacture those materials in the real application could be really challenging. And lastly, I'm going to talk about some of the ongoing work. We just put the paper, we just submit the paper, but before that, we actually put it on archive so you guys can take a look if you're interested. So we are trying to combine combustion with machine learning and to understand the chemical kinetics. And for those of you who are interested in chemical kinetics or laminar flames, chemistry, etc., you might be familiar with the Lu and Law diagram that predicts how the reaction, number of reaction scales as the mechanism goes larger and larger, as the species goes larger and larger. It's actually computationally, it's almost impossible to manually build the chemical kinetic models. And how we can computationally determine the pathways and the kinetic rates are very challenging. And for those of you who are still in grad school, it might take you the entire PhD to build a new model. So we were thinking, okay, since machine learning is developing so fast, so rapidly, and it has been proved to be effective in many areas, can we bring some of the techniques from machine learning to study chemical kinetics in combustion? actually using computer to aid the design of kinetic or kinetics is actually not new. For example, at MIT, we know Professor Bill Green is developing this RMG method and try to form a database of all possible reaction pathways, and then down selecting a compact set of reactions that are most feasible ones. However, this approach requires our knowledge on the possible reaction ways. So we need to specify certain forms. We need to know, we need to have certain expert knowledge. Another type of attempt is that instead of giving you all the possible pathways, we just give you the general form, right? This is a forward reaction. This is a backward reaction, etc. You can tell the reaction rate of certain species. However, when you optimize this, you actually in the literature, people have used the evolution algorithms or the genetic algorithms to optimize it. Such optimization algorithm is helpful for small systems. However, since we're going to deal with thousands of reactions and tens of thousands of parameters maybe, it's difficult to optimize a large-scale network. And we know in the deep learning community, they are good. There are tools that are good at optimizing large-scale nonlinear network. And in our work, we're just trying to explore the possibility of bringing some of the ideas and combine them with our knowledge on the chemical kinetics. Just a very brief summary of the fundamental of deep learning is that in the deep learning, what we really want to do is form a neural network model that can connect the input with the output. To do that, there are essentially two steps. The first one is the forward prediction. So all of these neurons are connected with the linear operations of the weights. And at the neuron, there is a nonlinear activation function that brings in the nonlinearity. And then everything linked together and predict the output. So this is a forward prediction. And after you predict the results, and you can compare the output with these results, or with the ground truth, and compute the loss function. And depending on the loss function and varying your parameters, those are the parameters you want to train for your neural network by taking the derivatives and then optimize those parameters. In the end, this process is called the backpropagation. In the end, you can optimize your neural network. And one of the most adopted method is the stochastic gradient descent. It's an optimization method, trying to figure out what these parameters are. So in our attempt, of course, we want to utilize this stochastic gradient descent to do the large-scale optimization. However, we also are interested in preserving some of the physical insights we obtained from combustion research. We want to remain some knowledge or keep some of the knowledge from the physical laws instead of using a purely black box modeling of neural networks. So a general example is this. If we have a reaction like this, A, B, C, D are the species. These coefficients there are the stoichiometric coefficient. There are two fundamental laws that we want to consider. The first is the law of mass action, which tells us how the reaction rate scales with the species concentration, rate constant, and the reaction order. And the second law is called the Arrhenius law, which tells us the dependence of the rate constant on the temperature. And give you a really simple example of this global reaction. It actually doesn't matter whether it's a global reaction or an elementary reaction. So we can encode this law of mass action into the neural network. What this is that you can write down the reaction rate expression like this, and then mathematically, you can rewrite it in this way. The advantage of doing this is that you can see in the parentheses, all of these multiplications turn into the linear operations. And we know, so the connections between the neurons are through the linear operations. And this nonlinear operation is the same as the activation in the neural network. So by doing this, we can use the input as the species concentrations, and then we can predict how the reaction rate or how the production rate of the species goes. So here is the result. So in terms of as far as the neural network is concerned, right? So all of these weights in the input layers, and this is the bias in the input layer. This is the activation energy, and these are the weights that needs to be trained. However, when we talk about the physics, actually all of these parameters has its physical meaning, right? The meaning is that you can, all of these weights correspond to the reaction orders. This bias corresponds to the rate constant. And these weights correspond to the stoichiometric coefficient. In this sense, we can actually explain what we can obtain from the neural network. So this is a law of mass action. And if we want to implement the Arrhenius law, we just need to further express this neuron into its constituents like this. Again, a linear combination. So for a single step reaction, we can just use a single neuron, one hidden layer, and to do this. Like I said, all of these rates correspond to the reaction order and rate constant. All of these weights correspond to the stoichiometric coefficient. And if we interpreted it, and we can combine this with our physical model, is that we can turn all of this into the kinetic parameters. We can turn, and this part tells us what the reaction pathways are, how different species are connected with each other, what are the products, what are the reactants. This is a single step reaction. And if we stack a lot of them together, we form the chemical reaction network, right? Now, one neuron is one reaction, and the number of the reactions matches the number of the hidden nodes in this hidden layer. And here, for the next, I'm just going to show you some of the cases. The first one is a synthesized network with 5 species and 4 reactions. You don't need to know all of the details, but take-home message is that you can actually see that this is a trained results, right? And this matches perfectly with the ground truth. We didn't tell the system what the reaction would look like. It just figured this out by itself. What we input is just the species time history on the concentration. Similarly, in this example, now we have the temperature dependence. So the Arrhenius law is activated here. And again, you can see all of the rates can be learned automatically from our algorithm. And you see some of these rate kinetics are not perfectly learned, but you can see it's very close. And the final example is on the biochemistry. So we are really bridging the combustion with other topics as well. So I actually do not understand the details of this. We took this from the literature, but this is the cell chemistry, and see how different proteins react and can send you the cell communication signals. And what's special with this is that you can see a lot of these activated species, they work as the catalyst. And it's oftentimes the traditional like mass conservation doesn't really apply here in this biochemistry side. And you can see our CRNN, the chemical reaction neural network, is really capable of learning these type of reactions. So the summary is that we can represent the chemical reaction network, we use a neural network by encoding the fundamental physics into that. And the biggest advantage of that is that we can obtain the reaction pathways as well as the kinetic parameters simultaneously. We do not need to tell them what the reaction pathway is and let it figure out the pathway of kinetic parameters. These two can be done simultaneously, right? And in the future is that, of course, it's difficult to handle more difficult, more complex chemistry. And how do we decide which physics goes into the model? How much physics we want to put into the model is still an open question. And later on, how do we deal with uncertainty measurements in the experiments? How do we deal with the unavailability of some difficult to measure species? Those are the questions that is going to be explored in future. And finally, I want to put a little bit of discussion here is that I know in the community, we are skeptical about using combustion, using machine learning in combustion. And some of you might think, okay, this is a regression, how it will not tell us physics. So what we are trying to do is that we still believe in the fundamental combustion knowledge would be very valuable. So what we were hoping to do is that we want to maintain some of the knowledges we got from the previous 100 years of combustion research, and also embrace the newly developed tools in machine learning. So we believe that the driving force for machine learning is really the backpropagation that tells us how to optimize things. And this is enabled in many open source deep learning frameworks as this one. And the GPU actually makes it very easy to do the batch processing and do the training very efficiently. So in order to embrace machine learning in combustion, the key is really to develop a deep learning framework for combustion, such that we can enable this backpropagation through our combustion models. Towards this goal, our group has recently developed a package called the Reac torch, which is a differentiable reacting flow simulation in PyTorch. And you can visit my group website, and under the software tab, there's a link to tell you how to find the code in GitHub. The main features, you can imagine, for those of you who might feel it's a little bit overwhelmed to hear all about these machine learning, you can imagine this package is almost the same as ChemKin. The only difference is it's the differentiable one, so that it enables the backpropagation. And it's written in the Python PyTorch, so you can utilize the existing packages relatively easy. Open source and GPU, so you should feel free to explore the capability of this code and let us know your feedback and if you want to collaborate on anything. And with that, I would like to conclude my today's talk. Is that I share with you some of our recent attempt try to bring UQ and materials science as well as machine learning with combustion. We are trying to bridge the frontier of combustion with other areas. There are successful attempts, there are many challenges, and there are many, many opportunities that for us to collaborate on, for us to explore. And basically combustion, a lot of the techniques developed in other areas can be used in combustion research. And we also want to think about how we can utilize some of the combustion knowledge and transfer that into other areas. For example, I know like Professor Zhu and the seminar speaker, Professor Prasinis in the spring, they will talk about how to utilize combustion to manufacture materials for energy storage or biosensing, etc. So I would say there are a lot of opportunities, and I will also try to report to the community when we have further the vents. With that, I would like to thank you very much for your attention, and I will be happy to answer any questions.
Well, thank you, Dr. Dou, for a very exciting talk that covers lambda flames, energetic materials, and all the way to machine learning, the newer stuff. Thank you. So now we're open for Q&A, and I've got a couple questions from the audience. So I'm going to ask on behalf of them. The first question is regarding sensitivity analysis. Can you explain why physically ESR and LFS sensitivity are in the same direction? Say if you change ESR to other quantities, such as flame temperature or flame thickness, will this, your sensitivity or the similarity still hold?
Yeah, this is a good question. Actually, the similarity in the sensitivity itself, qualitatively, this has been explored in previous literature, maybe in the past 10 or 20 years. People understand that. The main reason is that, you know, if you look at the reactions, most of the reactions are the very important chain branching reaction, the H2, the chain branching reaction, as well as the heat release reaction. So that makes perfect sense. Why because you know, in laminar flames, the ESR and the laminar flames are to the first order sensitive to the heat release reactions. And also in our later test, we also see that the temperature actually scales very well with ESR, the extinction strain rate. So they share the same reaction sensitivity directions very clearly.
Okay. All right, thank you. The second question is regarding energetic materials, especially aluminum combustion. So the question was, we have aluminum dust explosion very often, which is a disaster. Are there any ideas to suppress the reactivity of aluminum particles, for example, to prevent possible ignition and explosion, such as delay the ignition time?
Yeah, of course. Actually, whether you want to make it faster or slower depends on your application and safety concerns. So actually, the question distilled down to how can we really control the reactivity of aluminum? So I think this can be done in several aspects. The first one is the composition of the oxidizer and the interface and mixing between the oxidizer and the fuel, as well as the mechanical strength and the other, like the inertial impact or the ESD, where you have the electrostatic forces, etc. So a lot of, like I mentioned today, is that people are developing different methodologies to synthesize the composites, as well as adding dopants, try to control the reactivity of the aluminum composites. And sometimes when you want to preserve it, you will have certain passivation layers at the surface. Sometimes you want to activate it, you might have some ligand built onto the surface. So those will be the techniques.
All right, thank you. One last question. Could the materials of the combustion chamber walls possibly have any effects on the combustion process in the combustion chamber? This seems to be a very general question. I assume this is regarding the energetics work.
So in our experiments, actually, it's actually very localized reaction, since it's not a homogeneous, like the gas phase reaction that your whole chamber is mixed with all of this. Instead, the reactants or the powders are in a very small amount and very localized. So I do not expect that the wall condition would influence the combustion of the energetic materials in our case.
Okay, excellent. Thank you. Well, due to time limitations, I'm afraid we have to stop over here. If you have more questions, please feel free to contact Dr. Dorr. And thank you for your participation. It's a wonderful talk. And I'm going to give the floor to Dr. Guangju to conclude.
Thank you, Li, for chairing the session. And Sili, you give a wonderful talk, and from that sensitivity analysis to materials synthesis and that machine learning. I found that machine learning is a very interesting area. I think that you provide a new thinking about how do we optimize that reaction rate, activation energy, and then the temperature power dependence all together. And I wonder that one question I would like to say that if we consider there are some reaction, for example, you have stoichiometric ratio, you have that reaction rate. Each of the reaction is a neuron, but in many combustions, the one reaction may have different potential wells. And then do you have to add a multiple neurons for the same reaction? And how do you address that in the future?
Yeah, that's a wonderful question. So I think one of our challenge, or one of our thought, is that how much physics we want to inform our neural network, right? You mentioned all kinds of knowledges we got from previous combustion knowledge, and what are the minimum needed to get implemented into the neuron is one thing. And specifically for deep learning-based optimization problem, actually it's a very clear goal-oriented problem. So you can guarantee the performance. So I might not say it in a very correct way, but the thing is that if we believe it's going to be with some form, but the neural network give us another result, do we trust the neural network, or do we trust our previous knowledge?
Yeah, I think that your conclusion is very powerful, that we need to bring new knowledge and new tools to the combustion field. And at the same time that the knowledge has to be in combustion, has to be transferred to other areas to create an impact. I thank you again for the very exciting talk. And I look forward to your video and then on the YouTube channel. Thank you very much.
Bye.
Everybody.
Yeah.
Thank you for the great talk.
Bye. Bye.